Basic electricity, direct current. Number 1, electron flow. You do it dozens of times every day. You turn on a light or an electrical appliance and you turn things off. What you are actually doing is allowing an electric current to flow or pass through a circuit by making a simple mechanical connection with an electrical power source. And when you turn something off, you're stopping the flow of electric current by breaking the connection with the power source. That source could be as small as a flashlight cell or as large as a power plant. But how does electricity flow, and fundamentally, what is it? You can learn the answer by examining the following concepts: electron flow, current, voltage, and resistance. And in this program, all 4 of these will be introduced. First, let's examine the electron flow.
Look around you. Everything, even the air you breathe and water you drink, contains electric energy. Here's why. All matter, whether solid, liquid, or gas, is made up of molecules that are unique to that particular form of matter. In turn, a molecule is made up of atoms. And it's the structure of these atoms that holds the key to the electron theory. For example, a drop of water is actually made up of billions of invisible water molecules. The chemical formula for a molecule of water is H2O. That is, 2 atoms of hydrogen and 1 atom of oxygen. Yet the atoms themselves are made up of even smaller particles. These subatomic particles are called protons, electrons, and neutrons.
In the simplest of all atoms, the hydrogen atom, the nucleus contains only 1 proton and an electron moving around it, but it doesn't have a neutron. However, in contrast, the atomic structure of carbon is more complex. A carbon nucleus contains 6 protons and 6 neutrons. There are also 6 electrons. These electrons occupy different fields of energy outside the nucleus. These overlapping fields are often described as shells, here represented by rings. Note that the electrons are in 2 different rings. The first ring has only 2 electrons, and the second has 4. The point of explaining atomic structure, and the point that is essential for you to understand, is that protons and electrons carry electrical charges. Protons carry a positive charge, indicated by a plus sign, and electrons carry a negative charge, indicated by a minus sign. Neutrons have no electrical charge and are neutral. And this leads to a fundamental fact of electricity, namely that like charges repel. Opposite charges attract. The negative charge of an electron is equal to but exactly opposite the positive charge of the proton. Finally, the attraction of these opposing charges creates an energy field called an electrostatic field.
When an atom has an equal number of protons and electrons, it is balanced or neutral and has no net electrical charge. It is important to note that some atoms are in fact not stable. They can readily lose or gain electrons, creating free electrons. And it's this action of losing and gaining electrons that enables them to become electrically charged. For example, if a neutral atom gains an electron, it will then have more negative electrons than positive protons. The atom will then have a negative charge. Atoms with negative charges are called negative ions. Keep in mind that in reality, electrons move from atom to atom in an instant. This graphic simulation slows down the action so you can follow along. On the other hand, if a neutral atom loses an electron, it will have fewer electrons than protons. An atom with fewer electrons than protons becomes positively charged and is called a positive ion. These positive and negative ions, or unbalanced atoms, can now attract or repel each other's electrons. Remember, like charges repel, while unlike charges attract.
Electricity, or an electrical charge, is produced when electrons move from one atom to another. This movement occurs because of the attraction of protons to electrons and the repulsion of electrons by electrons. This movement is called electron flow. Electric current is created by the movement of many electrons between atoms.
A basic unit of measurement in electricity is the coulomb. Just as 12 inches equals a foot and 16 ounces equals a pound, it takes 6.24 billion electrons to equal 1 coulomb.
Electric current is measured in amperes. Amperes are calculated in coulombs per second. That is, 1 coulomb of electrons moving past a specific point in a circuit in 1 second equals 1 ampere of electrical current. For example, if 4 coulombs of electrons were to pass through a single point in a circuit in 2 seconds, you'd have 2 amperes of current. Therefore, current in terms of amperes equals coulombs divided by seconds. This statement can be expressed using abbreviations called the International System. Capital C stands for coulombs. The capital A is for amperes. Capital I is for electric current, and a small t stands for the time in seconds. Therefore, the equation reads, current I in terms of amperes A equals coulombs C over seconds, small t. From here on, you'll learn the International System of Electrical Abbreviations as each concept is introduced.
Getting back to the electric current, to create a steady flow or movement of electrons, there must be a constant electrical pressure. This pressure is called electromotive force, abbreviated EMF. EMF may come from a variety of sources. For example, a 1 1/2 volt standard flashlight cell, a 6-volt lantern battery, or a 12-volt car battery. In addition, EMF is also available in your home in the form of a standard 120-volt electric outlet. And for large appliances, like an electric dryer, there should be a special outlet with a 240-volt capacity. In industry, 240 and 480-volt outlets are common for use with large motors that run heavy machinery. However, since you'll be using a battery, let's take a careful look at it as one source of EMF.
At one terminal of the battery, there are atoms with an excess of electrons called the negative terminal. And at the other terminal of the battery, there are atoms which are deficient in electrons, called the positive terminal. The attraction of opposing charges between the negative and positive terminal is what eventually creates EMF and thus current. The imbalance of electrons between the two terminals is known as potential difference. The symbol for potential difference is a capital E. E, or potential difference, can only exist if there is a negative charge at one terminal and a positive charge at the other. The unit for measuring electrical energy is a joule and is abbreviated with a capital J. If you divide the number of joules, that is, electric energy available from the power source, by coulombs, The result will be the amount of potential difference in terms of volts.
The volt is the basic unit of measurement for potential difference. It's named after Alessandro Volta, and the abbreviation for volts is a capital V. The formula for volts is simple. Potential difference, E, in terms of volts equals joules divided by coulombs. Using abbreviations and symbols, E in terms of V equals J divided by C. Another way of describing voltage would be to say it measures the electric pressure available to push electrons from one atom to another, thereby creating current.
The final concept of electricity is resistance. It is the opposition to electron flow, and its symbol is a capital R. Materials with low resistance are called conductors of electricity. Examples of good conductors are copper, silver, and aluminum. Conversely, materials with high levels of resistance are called insulators. Rubber, ceramic, and bakelite are good insulators. Because current is the movement of free electrons, the more free electrons available in a material, the less resistance. Hence, the better it is at conducting electricity. And the opposite is true for an insulator material. That is, fewer free electrons means more resistance.
The unit of measurement for resistance is an ohm and is represented by the Greek symbol omega. It's named after a mathematician, George S. Ohm. Here's another formula, and it's very much like the ones for current and voltage. However, it's one of the most important formulas in electricity. It states that resistance in ohms equals volts divided by amperes, and it's called Ohm's law.
For example, if 6 volts were applied to a device and 2 amperes of current flow through it, the device would have a resistance of 3 ohms. More practically speaking, a common toaster has a rating of 120 volts and 6 amperes. Plugging in the numbers, you get 120 divided by 6, which equals 20 ohms. You'll learn more about Ohm's law later on. Let's stop here and review what you've been shown.
Number 1. Electron flow is the movement of electrons from atom to atom. The movement of many electrons is what creates an electric current.
Number 2. Voltage is a unit of measurement. Its symbol is a capital V. Voltage measures the potential difference E between a negative and positive electrical source.
Number 3. Resistance R is the opposition to electron flow. The unit of measurement for a resistance is an ohm, and the symbol for ohms is an omega.
The 4 concepts that were described in this program, electron flow, current, voltage, and resistance, are the building blocks on which you'll build your entire understanding of electricity.